let us see some nice applications of the mean value theorem. I will first state one property of the derivative that you are no doubt familiar with. The sign of the derivative determines whether the function is increasing or decreasing, and you can use the sign to predict it. Let's make this into a rigorous statement. Proposition let f be continuous on closed interval a b, differentiable on open interval a b, and of course a is less than b. Assume the derivative is greater than 0 on AB. Then f is strictly increasing on closed interval AB. To clarify, this strictly increasing just means that if x is less than y, f of x is less than f of y. Right? X comma y coming from AB. This is just a clarification of what it means for a function to be strictly increasing. Similarly, I leave it to you to formulate what is strictly decreasing, what is just increasing, and what is just decreasing. Just increasing and just decreasing will just have less than or equal to here. Okay? So let me just erase that less than or equal to so that there is no confusion. Proof. Well, the statement is long and the proof is, I think, only maybe even shorter. So suppose a less than or equal to x, less than y, less than or equal to b. Choose some xy in the closed interval ab. Then f of y minus f of x is equal to f prime of c into y minus x, where this c is coming from open interval xy. Right? This is just what the mean value theorem says. This is just the mean value theorem. Okay? But that just means fy minus fx is greater than 0 if y is greater than x. Right? Simply because f prime of c is always greater than 0. Okay? So I should write greater than 0. Because f prime of c is greater than 0, you immediately get the result. Okay? So similarly you can formulate results for f prime of x greater than or equal to 0, f prime of x less than 0, f prime of x less than or equal to 0. Here you will conclude that f is increasing, here you will conclude that f is strictly decreasing, and here you will conclude that f is decreasing. Okay? Sometimes to emphasize the distinction between increasing and strictly increasing, we may write weakly increasing. Okay? That's some terminology used by some people. This just means f of x is less than or equal to f of y if x is less than or equal to y. So I leave it to you to formulate and prove these easy results. They are nothing new. They're exactly the same. We have a nice corollary of the previous proposition. The corollary says the following. If f is continuous on closed interval ab and differentiable on open interval ab, then and if f prime of x is 0 on AB, then f is constant. Well, this is a rather easy corollary. Once you have established all the results for f prime of x greater than or equal to 0 and so on, you can apply this proposition that we just proved to both conclude that f is increasing as well as decreasing, which leaves f with the only option of not changing at all. Okay, so this is one interesting set of results that follow immediately from the mean value theorem. Now I want to introduce some results about the sign of the second derivative. So what is the second derivative? Well, if f is differentiable on a, we have, of course, we can consider this function f prime from a to r. Okay, so this just gives the derivative at every point. Well, we can define the second derivative. The second derivative f, we write it as double prime, which is just f prime prime whenever it exists. Okay, note we get several simple corollaries. If f double prime exists at every point of a, then f prime is automatically continuous at every point of a, and so on. Similarly, we can inductively, that's a better thing to use, inductively define higher order derivatives. Now this prime notation for derivatives quickly starts to become very, very annoying once you cross 3. Even 3 itself looks a bit ugly. I'm writing something like f triple prime of x. Okay, so better notation is just this. We will use fk to denote k times derivative. Okay, or the kth derivative, that's kth derivative. Okay, with the additional thing that k equal to 0 just gives back the function. This is just a convenient convention. So f0 is just f, f1 is f prime, f2 is f prime prime, and so on. Okay, so the k indicates how many times you are differentiating the function. Now, one important notation, since it's important, I'm going to put it in green notation. Let a b be an open interval a less than b, then ck of ab, this is defined to be the collection of all functions defined. For convenience, let me not put the braces because it's a bit long. Collection of all functions f from open interval a b to r such that fk exists and fk from ab to r is continuous. This is important. So ck of open interval ab is the collection of all functions f from ab to r such that fk exists and fk is continuous. So if you think about this definition for a couple of moments, you will realize that automatically fk minus 1 exists because that's the way fk was defined, right? For fk to be even defined, fk minus 1 must be defined. So automatically f1, f2, f3 dot till fk minus 1 is automatically defined just because I'm saying that fk exists. Okay, so this fk exists is automatically asserting that all the lesser derivatives also exist, and fk should be continuous. There is no notation for just functions whose kth derivative exists. To the best of my knowledge, there is no notation for that, but there is a notation for this. Functions whose kth derivative exists and the kth derivative is continuous. Just for convenience, I'm using open intervals. I don't want to deal with the closed interval case when I consider such higher order derivatives. Okay, there's no theoretical issue. You can define it just like that. It will just not come up much in our study. Okay, now our goal is to interpret sine of f2. Sine of f2. Okay, so for this, first some basic geometry. Suppose I have a curve that looks like this. Such a curve is called convex upwards. All of you are familiar with convex and concave lenses. This is called convex upwards. This just means that if I take 2 points on the curve and consider the line joining those 2 points, then the curve lies beneath that line always, at all points. Okay, so the opposite of this is something that looks like this. Okay, and here if you join 2 lines, it's not the case that the curve is below the line. That is not happening. Now you might ask, why don't I just call it convex and call this concave? There is a reason why we say convex upwards. Just think for a moment. This notion of concave or convex sort of depends on which direction you are looking from. A surface that is concave, if you look at it from the opposite direction, will become convex, and vice versa. So these are notions that are not defined independent of how the observer is looking. So it's better to always write convex upwards. Okay, let's define this formally. Definition: let I be an interval. I'm not specifying whether it's closed, open, half closed, nothing like that. And f from I to R be a function. Let a comma b be elements of I, or rather we say f is convex upwards if for all a comma b in I we have f of x is less than or equal to f of a plus f of b minus f of a by b minus a into x minus a. This is for all x in the open interval AB. Okay, so it's convex upwards if the value of the function in any subinterval is less than or equal to the line joining the points a f of a and b f of b, whose equation is given by this. So this must be true for any pair of points a comma b in I. So to clarify, I can just write a is less than b. Okay, choose a comma b in I such that a is less than b. This must be satisfied. If the inequality is strict, then we say strictly convex upwards. So now let's prove a theorem that relates this notion of convex upwards with the second derivative. So just let's see the picture again. If the function is sort of convex upwards, then observe that if you look at the various tangent lines to the curve, those seem to be sort of moving towards the left, right? So this will be captured by the second derivative being greater than 0. So let's see that theorem. Let f from close interval ab to r, or I don't actually require, let it be. Let f from ab to r be a function such that f is twice differentiable on open interval ab, and assume f double prime x is greater than 0 for all x in ab. Then f is strictly convex upwards. Okay, now proof. Let c comma d belong to this open interval ab. Let c comma d belong to the open interval ab. Okay, now consider the function g of x defined to be f of c plus f of d minus f of c by d minus c into x minus b x minus c minus f of x. Now this function should ring a bell. This is very similar to the function that we considered while proving the mean value theorem. So what I'm essentially doing is I'm considering the function, the line passing through the points c f of c and d f of d, and I'm subtracting f of x from this. As can be guessed, our goal is to show that this function g of x is greater than 0 for all points x in the interval ab. Okay, so this function g is defined from cd to r. Okay, now how am I going to show that this function g is actually strictly greater than 0? Well, apply the mean value theorem to f on the close interval cd. This gives e in the open interval cd such that f of d minus f of c by d minus c is equal to this f prime at e. Okay, so consequently g of x just becomes f of c plus f prime e times x minus c minus f of x. Therefore g prime x is just f prime e minus f prime x. Okay, now observe that e is in between the points c and d. So apply the mean value theorem on the interval xe when x is less than e. again, so we are applying the mean value theorem again, which we can do because we know that the second derivative exists. Okay, so because of this, you will get f prime of e minus f prime of x is sum f prime of f double prime of L times e minus x. E minus x. Okay, now this has got to be greater than 0 because e minus x is greater than 0 and f double prime by hypothesis is greater than 0. My L looks like an e, so let me just change it. Okay, so this is greater than 0. So what we have concluded is that g prime x is greater than 0 on the interval not just on the interval, c comma e, right? X could have been any point. X could have been any point in the interval c comma e, and we could have applied this argument to conclude that g prime x is greater than 0 here. Okay. Similarly, applying mean value theorem to f prime on the interval e comma d, we conclude that on e comma d, f double g prime of x is less than 0. Okay, so what we have done is we have applied the mean value theorem for a point x that lies between c and e to the function f prime, and concluded that g prime x has to be greater than 0 on CE. Similarly, we apply the argument to the point e, any point x coming from the open interval e comma d, and we get g prime of x is strictly less than 0. Now, how does this help us? Let's go back and refresh our memories as to what this function g is. Observe that at the point x equal to c, you get a grand 0. Right? You get a grand 0. And observe again that at the point x equal to d, you get a grand 0 yet again. Please check that. When x equal to d or x equal to c, you get 0. So, g of c is equal to g of d is equal to 0. Now, what does this tell us? This tells us that g is increasing on the interval c comma e. So, in fact, strictly increasing because we have concluded that g is greater than 0. We have concluded that g prime is greater than 0. So, it's strictly increasing on c comma e. So, g of x is greater than 0 on c. Right? So, by continuity, and furthermore, g is strictly decreasing on the interval e comma d, and g of d is 0. Okay, that we already know. This forces g to be greater than 0 on CD. Why is that? G of c is 0. The function is increasing from c to e. So when it reaches c, it will obviously be strictly greater than 0 again. And from there, it can never reach 0 in the interval e comma d, simply because it's decreasing, and at the endpoint d, it is still 0. So this forces g greater than 0 on c comma d, including at the point e. You might think that the point e is an exception, but the argument we have given rules out the possibility that g of e is 0 as well. So g is strictly greater than 0 on c comma d. In other words, the function we considered, g of x, is greater than 0, which is just going to say that f of x is less than or equal to f of c plus, not less than or equal to, f of x is less than f of c plus f of d minus f of c by d minus c into x minus c for all x in CD. In other words, f is strictly convex upwards. Strictly convex upwards. So this proof required a little bit of delicate analysis. We had to apply the mean value theorem twice, but now we know that the derivative, second derivative, the sign of the second derivative can help us determine how the function is sort of turning. Okay, so I leave it to you in the exercises to formulate versions of this when you have other sorts of inequalities. Instead of greater than, you have less than, f double prime is less than 0, less than or equal to 0, greater than or equal to 0. These are all trivial modifications of this. So this concludes one set of applications of the mean value theorem. We will see some more later on, especially Taylor's theorem. This is a course on real analysis, and you have just watched the module on applications of the mean value theorem.